Welcome to my lectures on thermodynamics. In my previous lectures, we were discussing about the displacement work, which is used in the first law of thermodynamics. And in today's lecture, let us shift toward the heat, because the first law states that change in internal energy of a system is equal to heat supplied plus work. We have elaborately discussed about the work. We will discuss about the heat now. So we can combinedly apply the first law after learning the heat, because heat and work are different forms of energy. Okay, let us go to the lecture. As we are discussing about the heat, there are different kinds of forms of heat, I can say. One is sensible heat, second is the latent heat. When we are calculating the heat requirements in a process, whether you have to see whether we are talking about the sensible heat or we are talking about the latent heat. In general, sensible heat means when heat is supplied to the system, you will see a change in temperature of the system. When you see the change in temperature, then it comes to the sensible heat. When you are supplying energy to the system, the temperature of the system is not changing, but you are giving energy to the system, then that kind of heat is nothing but the latent heat. So that is why energy transfer with change in temperature comes under sensible heat. Energy transfer at constant temperature, it comes under the latent heat. The latent heat means, see, when you are take an example of the, because I have pictorially represented, schematically represented, there is some system, you can consider this as a system. I have a piston and cylinder assembly. There is some ice is there in the system. The piston indicating that I am doing the things at some constant pressure. Let us start the lecture. Take the system, that means system is a block of ice inside the cylinder. The ice, as we know, it starts at 0 degree centigrade. If I take an example, if I take a block of ice at 0 degree centigrade, what we are doing is supply the heat. Okay, when you start supplying the heat to the system, what happens? The ice will start melting, right? Still, if you go to the melting process, means there is some amount of ice will convert to the liquid. You are supplying the heat, but the temperature is not changing. See, initially it's a block of ice. It is now ice plus water. Because when you are supplying the heat, there is system has taken the heat in melting the some part of ice. During this melting process, you won't see the change in temperature. But where this energy is going? Energy is going in the form of latent heat, where the energy, earlier it is ice, now it is some part of the ice has converted to the water. That means energy has taken by the water. During this melting process, there is no change in temperature. If you supply more amount of heat, this remaining part of ice will completely convert to the liquid. Still, the temperature won't change. Even though you are supplying heat, the temperature of the system will not change during the melting process. That is why it is called the heat transfer during this phase change from block of ice to the liquid, which happens at same temperature. That is called energy has been transferred, and this energy is used in converting the phase of from ice to the liquid. That is called, it's a latent heat. 1, 2, 3, during this process, the energy whatever we have supplied, that is called the latent heat, because during this phase change, there is no change in temperature. That is why this comes under heat transfer in enthalpy of melting. Okay, that's in the form of latent heat. And you can see, after you are reaching the liquid state at 0 degrees centigrade, if you still try to heat the system's temperature, that means liquid water temperature, will start to rise. For example, take 25 degrees centigrade. That means once you see the change in temperature after you supply the heat, that means now you can see the change in temperature has happened. This comes under the sensible heat. That means wherever you supply the energy, you can detect that supply of energy in the form of change in temperature. This comes under the sensible heat. That means which can be sensed with the changes in the temperature of this particular system. Even if you still further heat the system, it will reach to, again, let us say 100 degrees centigrade. From 0 to 25, example 25 to 100, you can see the changes in the temperature till 100. From 0, 25 and 100, between this you can observe the changes in the temperature. That is, everything comes under the sensible heat. Once you reach the 100 degrees centigrade, if you still supply the heat, what happens? Some part of the liquid will turns to the vapor. When some part of the liquid turns to the vapor, it's called the vaporization process. And now the second latent heat again came. See, from liquid, pure liquid, to liquid plus vapor, everything happens at the same temperature. That means even though you are supplying heat, the temperature is not changing. Now the phase transformation is changing from liquid to liquid plus vapor. If you still supply the more amount of heat, the entire liquid will convert to the vapor. So during this liquid to the vapor state, whatever the energy you have supplied, you won't see the change in temperature. Only thing is, everything comes under the latent heat of evaporation. This all, again, these three things comes under the latent heats. Okay. And let us, if you further heat the system, now the vapor temperature starts rising from 100, example, to 150. Now you can see whatever the heat you are supplied or energy supplied to the system, now you can observe the changes in the temperature after it is reaching the vapor state. Now again, you have to apply the principle of sensible heat to calculate how much amount of heat that is transferred. So the system, you can see there are some situations where the latent heat is given. There are some situations where sensible heat you can able to find out. That is why you have to for you to calculate how much amount of heat that has been supplied during this entire process, we have to use some example. Let us further go to the example state. See, everything happens at a constant pressure. You can see I have maintained the same pressure because I have applied same amount of pressure, and inside also pressure P1, imagine you have taken 1 atmosphere pressure is there everywhere. Okay, that means I am transferring the heat at the same pressures, okay, because and temperature is changing, because that will be useful in our further calculations. So whatever the process you want to calculate the heat requirements can be calculated with the 3 different ways. One is mCp dt. This is the formula used. M is the mass, Cp is the specific heat capacity at the constant pressure, dt is the temperature change. So as you know, just now we have discussed, wherever the changes in temperature is observed, okay, then everything goes to these 2 formulas, because here if you supply the heat, the temperature is changing here from 0 to 25. That means by observing how much temperature has been raised, based on that you can calculate mCp dt. If it happens, if the entire process happens at the constant pressure, you take Cp. If the heat transfer happens at a constant volume, that means pressure is not changing. Now I fixed this much amount of volume everywhere. The pressure will change here. So either you supply the heat in case of at constant pressure, or you supply the heat at constant volume. If you supply the heat at a constant pressure, use mCp dt. If you supply the heat at constant volume, use mCv dt. For the liquids, Cp almost close equal to Cv. Okay, and the third is latent heat. You can see these 1, 2, 3, whatever the heat is supplied, the temperature is not changing during the process. Wherever this kind of situation comes, you have to calculate how much amount of heat that is supplied is in the form of latent heat. So either you sensible heat, Cp dt, Cv dt, second is the latent heat. That means we have to know the values, okay? Enthalpy of evaporations, enthalpy of fusions, okay? We have to use that specific internal energy, okay? Latent heat of melting, latent heat of vaporization, latent heat of sublimation, latent heat of fusion. These are the values we have to use to calculate how much amount of heat that has been gone into the process. So let us calculate how much amount of heat that is gone from taking the ice from 0 degrees centigrade to the vapor at 150 degrees centigrade. Let us calculate, okay? So that is why I calculate the total heat transferred during the heating of ice, okay, from 0 degrees centigrade to 150 degrees centigrade at a constant pressure process. Imagine 1 kg of ice is there, okay? Let us apply. What is the first process that is taking place? Here 1, 2, 3 comes under the latent heat. That is why the total amount of heat that starts with how much amount of mass and what is the latent heat of melting. Second, mCp of water dt. Second thing, from 0 degree centigrade, example 0 to 25, 25 to 100, that means liquid temperature has raised. So from 0 degree centigrade to 100 degree centigrade, use the latent heat, sensible heat equation like mCp of water dt from 0 degree centigrade to 100 degree centigrade. What happens after this? During 5, 6, 7, that is called comes under the latent heat, because here the temperature is not changing. Now you have to apply again the latent heat of vaporization. So plus, okay, this m, okay, m is 1, don't worry, plus latent heat of vaporization, how much amount of mass is there, and multiplied by what is the latent heat of vaporization. After completely converts to vapor, now from 100 to 150, again it comes under the sensible heat. So that is why Cp of water vapor into Cp of water vapor, okay, water vapor from 100 to 150. Now this is how we can able to calculate how much amount of heat that has been supplied to the system. As I know, given the values, Cp of water is 4.18 kilojoule per kg per degree centigrade. Enthalpy of melting, okay, why we have taken enthalpy? Internal energy is also there, enthalpy is also there. Then why I have taken specifically enthalpy of melting? Why can't I take the enthalpy of, internal energy of the melting? So in my next lecture, I will give you clarity why the enthalpy of is important than the internal energy. So let us, I know the formulas, m equal to 1 because mass is 1 kg, rest enthalpy of melting is given, enthalpy of vaporization is given, Cp of water vapor is given, and m is 1 kg. And in majority of the cases, Cp is constant. So you can take out from the integral, okay. If you take Cp is a constant, it comes out of the integral. Integral 0 to 100 dt is nothing but 100 T from 100 to 0 degrees centigrade. That is why Cp into 100 minus 0. Here also Cp of water vapor, if it is constant, you can take out of the integral. If you take out of the integral 100 to 150, what is dt? Is 150 minus 100. So once you put all the values and if you calculate how much amount of heat is supplied during this entire process is 3101.55 kilojoule per kg, because we have taken basis of 1 kg. That means every kg during this process, the amount of heat that gone into the system is 3101.55 kilojoules. This is how you can able to apply the equations of heat, in calculating the heat requirements in a process. In my next lecture, I am going to give you the clarity of enthalpy and internal energy. Okay, thank you for the listening to me.